If you start at the center of our solar system and fly outward, you pass the scorching rocks of Mercury and toxic clouds of Venus. Then, exactly 150 million kilometers out, you reach the third planet, Earth. For centuries, humans looked out at the horizon and assumed this world was a flat disk. They drew maps with steep edges, convinced that if a ship sailed far enough, it would simply fall off into the void. Earth's rotation creates centrifugal force, an outward push that constantly pulls the equator outward while the poles compress inward. You can measure this distortion. The equatorial diameter is 12,756 kilometers, but from pole to pole, it is only 12,714 kilometers. Because of that 42-kilometer difference, Earth is not a perfect sphere. In geometry, this specific shape is called an oblate spheroid. Geologists also call it a geoid, a term that literally translates to Earth-shaped. The shape of our planet is a direct physical reaction to its rapid movement through the vacuum of space. You don't need a spaceship to prove this geometry. You can observe the curvature right from the surface. Stand on a beach and watch a ship sail toward you from the horizon. You will always see the top of the mast first. As the ship gets closer, the deck appears in the middle, and finally the heavy hull comes into view. If the ocean were perfectly flat, the entire ship would be visible the whole time, starting as a tiny dot and growing larger in proportion. Instead, the hull remains hidden behind the physical curve of the water. In the 19th century, scientists tested this exact phenomenon with the Bedford level experiment in England. They found a perfectly straight 5-kilometer stretch of canal and drove 3 identical poles into the water, spacing them evenly. When they looked through a telescope from one end to the other, the middle pole appeared slightly higher than the outer two. The water between the poles was physically arching upward. The ground feels flat to us because of our small size relative to the planet, but basic geometry reveals the curve over a distance of just a few kilometers. The evidence becomes even clearer when you look up at the night sky. At the North Pole, the pole star sits directly above your head at a 90-degree angle. As you travel south, that star steadily drops toward the horizon until the viewing angle reaches 0. That gradual shift only happens if you walk along an arc. And during a lunar eclipse, we can literally see our own shadow projected onto the moon. No matter how Earth rotates, the shadow creeping across the lunar surface is always a perfect circular arc. Only a sphere casts a circular shadow from every orientation. The math on the ground and the mechanics in the sky perfectly validate the shape we now photograph from orbit. But being an oblate spheroid does not make Earth special. Mercury and Venus are also rocky spheres, yet their surfaces are completely hostile to biology. The distinction lies in our exact position. Earth orbits within the Goldilocks zone, a narrow region around a star where conditions are neither too hot nor too cold. This precise distance gives us a stable global average surface temperature of 17 degrees Celsius. That specific temperature allows liquid water to persist over billions of years. Water covers 71% of Earth, functioning as a massive planetary thermal regulator. This global thermal map visualizes how water absorbs and distributes energy. Liquid water can hold enormous amounts of heat without its own temperature rising significantly. During the day, the oceans soak up the sun's harsh energy, keeping the land masses cool. At night, they slowly release that stored heat, preventing the continents from freezing over in the dark. Wrapping all of this is a thin, protective shell of gas. It consists mostly of nitrogen and oxygen, but the critical upper boundary contains the ozone layer. Ozone is a gas molecule made of 3 oxygen atoms that specifically absorbs destructive ultraviolet radiation from the sun, shielding the surface below. This flowchart maps the planet's self-sustaining nutrition cycle. Solar energy allows plants to pull carbon out of the air. Animals consume those plants, moving the carbon through the food chain. When organisms die, that carbon settles deep into the lithosphere, the rocky outer crust of the planet, forming ocean sediments and fossil fuels, before eventually cycling back out. From the geometry of the spin, to its distance from the sun, to the chemistry of the air, everything works in tandem. Earth operates as a highly complex, self-sustaining machine. Look out into the vastness of the cosmos, and you will mostly find an empty, freezing, completely lifeless blackness. Where there is matter, it is often incredibly hostile. Our own local neighborhood is dominated by the violent, burning radiation of the sun. Yet, hanging in that same freezing void is a single, vibrant anomaly, a fragile sphere of blue and white that somehow harbors life. Earth's habitability is the result of a precise physical recipe, a specific set of environmental conditions that we can trace through observation. For most of human history, people assumed the Earth was a flat disk with dangerous, steep edges. It was a logical conclusion based on what they could immediately see. But as people began to travel, they noticed a discrepancy. The sun rises and sets at entirely different times depending on your location on the map. By the 5th century, scholars like the Indian mathematician and astronomer Aryabhata realized what this meant. The Earth is actually a rotating sphere. Proving this required humanity to stop trusting their immediate flat surroundings and start finding concrete visual evidence in the environment. You can see this evidence for yourself at any seaport. If you stand on the shore and watch a ship approach from the distance, you will always see the very top of the mast peek over the horizon first. As it gets closer, the deck appears, and finally, the hull comes into full view. If the ocean were completely flat, the entire ship would simply fade into view all at once, just getting larger as it approached. We can also look up. During a lunar eclipse, the Earth passes directly between the sun and the moon, projecting a shadow. The shadow our planet casts across the lunar surface always takes the shape of a perfect circular arc. Whether tracking a wooden ship across the water or measuring a shadow across the moon, the physical evidence points to a curved, spherical surface. But the Earth is not a perfect, mathematically exact sphere. Because the planet spins rapidly, it generates centrifugal force, pushing outward from its middle. This force causes the equator to bulge, making it 42 kilometers wider across the middle than from pole to pole. Scientists call this squashed shape an oblate spheroid, or a geoid. This bulging shape ensures that sunlight hits the planet at different angles. The equator receives direct, intense heat, while the poles receive slanted rays that must travel further through the atmosphere, an imbalance that drives the world's weather and wind. Shape is only the first part of the recipe. The second is our precise location. Earth sits in a narrow green band of the inner solar system called the Goldilocks zone. At 150 million kilometers from the sun, our average temperature is 17 degrees Celsius, warm enough to keep water from freezing, but cool enough to prevent boiling. Because we sit in this exact temperature pocket, the Earth can hold on to the primary ingredient for life, huge oceans of liquid water. Water covers roughly 71% of the Earth. These massive oceans act as a giant thermal regulator, absorbing enormous amounts of heat during the day and releasing it at night to prevent the surface from freezing. And the final ingredient is our atmosphere. This thin mixture of nitrogen and oxygen acts as an insulating blanket, keeping the planet warm while the ozone layer blocks harmful ultraviolet radiation. The combination of an optimal orbit, liquid oceans, and a gas shield transforms a barren rock into an active life support system. The solid rock of the lithosphere, the water of the hydrosphere, and the air of the atmosphere do not exist in isolation. They constantly interact. Where these elements meet, they create a single, continuous system known as the biosphere. This is a thin, 15-kilometer zone where every living organism exists. Every leaf, animal, and drop of mist in this forest is the direct result of that exact physical recipe: the spinning geoid shape, the Goldilocks distance, and the protective water and air shields. Ultimately, Earth is defined by this delicate combination. It provides the exact conditions needed to be our home.
You know, for most of human history, the shape of our world seemed, well, pretty obvious. But what if everything we saw with our own eyes was actually wrong? Today, we're going to trace the journey from ancient myth all the way to modern measurement to uncover the true and surprisingly complex shape of our home planet. For thousands of years, the answer just seemed so clear. I mean, just look around. The ground under our feet is flat. So early cultures imagined a flat disk, and a lot of them were genuinely afraid that if you sailed too far, you might just fall right off the edge. But was this gut feeling, this intuition, actually correct? Long before we had satellites or spaceships, a few brilliant minds out there dared to question what everyone else just took for granted. And they weren't just guessing. They were looking for clues, real clues that pointed to a much stranger and much rounder reality. So who were these first challengers? Well, you have to go all the way back to the 5th century, where the Indian astronomer and mathematician Aryabhata argued that the Earth wasn't just a sphere, but that it was also spinning on its own axis. Then, a century later, the Greek philosopher Pythagoras came to a very similar conclusion. Now, these weren't wild guesses. These were ideas based on watching the stars and using logic and math, and they planted the seeds for a total revolution in thought. So, how did they start to prove it? Well, it's kind of like a detective story, where all the clues were hiding in plain sight the entire time. Let's take a look at the evidence that really began to build the case for a round Earth. The very first clue is something anyone can see at the beach. If you watch a ship sailing towards you from the horizon, you don't see the whole thing at once. First, you see the very top of the mast. Then, the sails or the funnel come into view. And finally, you see the hull. Now, if the Earth were flat, the ship would just start as a tiny speck and get bigger. This top-down appearance is undeniable proof that it's actually traveling over a curve. Okay, this next one wasn't just a casual observation, it was a full-on experiment. Over in England, along this perfectly straight 6-mile stretch of canal, they set up 3 poles of the exact same length, each 5 kilometers apart. When they looked through a telescope from one end, the middle pole always looked higher than the other 2. And there's only one way that can happen. If the poles are sitting on a curved surface, with that middle one right at the highest point of the arc. Another huge clue is written right in the stars. Polaris, the North Star, sits almost directly above the North Pole. So if you're standing there, it's straight overhead, a 90-degree angle. But as you travel south, you'll see that star sink lower and lower in the sky. By the time you reach the equator, it's sitting right on the horizon, at 0 degrees. This constant change in angle is only possible if you're moving along the curve of a giant sphere. And now for what might be the most powerful piece of evidence, Earth's own shadow. During a lunar eclipse, our planet passes between the sun and the moon, and it casts a shadow. And that shadow is always a perfect circular arc. Now, a flat disk could cast a round shadow, but only from one very specific angle. The Earth's shadow is always round, no matter how it's oriented. That is the cosmic smoking gun for a spherical planet. So, case closed, right? The Earth is a sphere. Well, not quite. As our tools for measurement got more and more precise, we discovered a little twist in the story. See, sphere is close, but it isn't the complete picture. When we measure the Earth very, very carefully, we find something fascinating. The diameter from one side of the equator to the other is 12,756 kilometers. But the diameter from the North Pole down to the South Pole is just a little bit less, 12,714 kilometers. That difference, even though it seems small, tells us our planet isn't a perfect sphere. The correct scientific term for this shape is an oblate spheroid. So what causes this? It's the Earth's own rotation. As our planet spins, something called centrifugal force causes it to bulge out slightly around the middle, the equator, and flatten just a bit at the top and bottom, the poles. You can almost think of it like a cosmic orange. And if you want to get even more precise, scientists use the term geoid. This literally means Earth-shaped, and it acknowledges that our planet isn't some perfectly smooth mathematical object. It's a unique, slightly lumpy oblate spheroid, shaped by its rotation and its own gravitational fields. Okay, so we've gone from a flat disk to a sphere to an oblate spheroid and now to a geoid. But why does any of this matter? Well, it turns out that Earth's physical characteristics are precisely what make it a home for every single one of us. The Earth's average temperature is a pretty comfortable 17 degrees Celsius. And that's because we orbit in what's called the Goldilocks zone. We're not too close to the sun and not too far away. We're just right. And this ideal temperature is what allows for the single most important ingredient for life as we know it, which is, of course, liquid water. A staggering 71% of our planet's surface is covered in it. That's what earned us the nickname the Blue Planet. And this water does more than just host life. It also acts as a massive climate regulator, absorbing huge amounts of heat during the day and releasing it at night, which keeps our temperatures nice and stable. We also live and breathe inside a protective bubble. Our atmosphere is this perfect mix of gases for life, mostly nitrogen and, of course, the oxygen we need to survive. And inside that tiny other gases slice, there's a critical component, the ozone layer. It shields us by absorbing the sun's most harmful ultraviolet rays.
So when you put it all together, you get the recipe for a truly unique planet. We've got the perfect distance from our star, which gives us an ideal temperature. That allows for oceans of liquid water. Then we have a breathable, protective atmosphere. And on top of that, a solid crust, the lithosphere, for life to actually take hold. It is an absolutely extraordinary combination of factors.
You know, our journey to understand our planet's shape is really a story about our own growing awareness, about going from seeing just a flat world at our feet to understanding that we live on this complex, living system that's just floating in space.
This long journey of discovery has revealed a world that is perfectly and perhaps uniquely suited for life. And knowing just how special and fragile this system is leads us to the most important question of all. Now that we understand our home, what will we choose to do to protect it? The answer to that? Well, it's going to define our future.